Okay, what I'd like to do today is review a little bit over Chapter 2, which is basically limits. So some things that you may or may not remember, one of them is called the sandwich theorem, or sometimes in other textbooks they call it the squeeze theorem. So let me write out what this theorem is. So if you have some function g of x less than or equal to some other function f of x, which is less than or equal to some other function h of x, for all x not equal to c, in some interval about c, and the limit as x approaches c of g of x equals to the limit as x approaches c of h of x is some number L, then the limit as x approaches c of f of x equals to L. So basically, just kind of picture these three functions, g, f, and h. So for some interval, meaning on whatever section we're looking at and thinking about, g is always on the bottom, f is always in between, and h will always be on top, okay, for whatever interval we're talking about. So kind of look and see what this first statement here says. It says that if the limit of g and h as x approaches some x value c equals to the same thing, then it's kind of going to squeeze f together. So it actually has to look something like that, for instance. Okay, so it's basically going to squeeze the function f right in between, and it forces it to be a particular limit. So maybe it'll make a little bit more sense if I show you this next example. Okay, so let's show that the limit as x approaches 0 of x squared sine 1 over x equals to 0. I kind of like these kind of problems where it says show, because that means you know it's true, you just need to have to prove to me that it's true. Okay? Now first let's just kind of stop and think for a second. What do you know about the sine function? Okay? We know that sine x is between 1 and negative 1, right? It oscillates back and forth, going up and down. So that should also mean that sine 1 over x is less than or equal to 1. Because sine of anything, no matter what it is, in this case now it's a 1 over x, must still be between negative 1 and 1. Okay. Now I know this isn't the one we're trying to figure out. We're trying to figure out the limit of x squared sine 1 over x. So what I'm going to do now in this extended inequality is I'm going to multiply each part of this by an x squared. So I'm going to have a negative x squared on the left-hand side, less than or equal to x squared sine 1 over x, and that's going to be less than or equal to a positive x squared. Okay, so now in terms of looking at the graph of this one, if you were to look at the graph of y equals to x squared, it looks something like that. Y equals negative x squared looks something like that. And if you actually pull up your graphing calculator and look at x squared sine 1 over x, it actually looks kind of like that. Okay, it kind of goes back and forth. It's a little bit skinnier. Now I want to prove that this limit equals to 0. You can look at it graphically and see that it is, but let's continue with this algebraically. Okay, so this is the right function that I have, x squared sine 1 over x. So now I want to evaluate the limit of each of these. The limit as x approaches 0 of a negative x squared should be less than or equal to the limit as x approaches 0 of x squared sine 1 over x. Should be less than or equal to the limit as x approaches 0 of x squared. Now what's the limit of the left-hand side of this? It's a 0. What's the limit of the right-hand side of this? also 0. So take a look and see what happens. This limit that we're trying to find out has been squeezed or sandwiched in between two other ones that approach 0, so it must approach 0 as well. Okay? So that's the sandwich theorem. Now the other thing I want to go over with you guys is something called end behavior model. And I'm going to go over the definition of it. So this one says that the function g is what we call the right end behavior model for f if and only if, hope you remember that from geometry, IFF, if and only if the limit as x approaches infinity of f of x over g of x equals to 1, and it is called the left end behavior model for f if and only if the limit as x approaches infinity of f of x over g of x equals to 1 as well. Okay? Oops, I'm sorry. X approaches negative infinity. It's the left end behavior model, so it's going to go to negative infinity. Okay, so let's kind of take a look at an example of when you would be asked for an end behavior model. And there are many sorts of answers for end behavior model. It's just sort of a generic one that we're looking for. So you'll see that in a second. Find an end behavior model for f of x equals 2x to the 5th plus x to the 4th minus x squared plus 1 all over 3x squared minus 5x plus 7. Okay? So basically, I want to find some other function g. So we need to find this g, so that when I divide f by that g, I get a 1. So it's kind of like a little puzzle. You're working backwards. So think about this. Limit as x approaches infinity of 2x to the 5th plus x to the 4th minus x squared plus 1 all over 3x squared minus 5x plus 7. Now it has to be all over some other function unknown. Now if we just focus on the top part of this function, or top part of this fraction, when you're evaluating the limit as x approaches infinity, which parts of this polynomial do we actually look at? You guys know? We don't actually look at the lower powered ones. We only focus on the higher powered ones. So we're only going to look at 2x to the 5th over 3x squared. Why? Because as x goes to infinity, x to the 5th power is way bigger than x to the 4th power in the numerator. In the denominator, x squared is going to be way bigger than anything 5 times x could be. So my end behavior model is quite simply going to be just 2x to the 5th over 3x cubed, or we can simplify that as x squared over, x squared 2/3 x squared, sorry about that. So that's my function g, and that's what we call the end behavior model. Okay, let's try another. So what if g of x, oh, I guess I can call it something else because I was calling it the end behavior model g. So let's use an h of x. What if I have some other function h of x, and it's equal to 2x cubed minus x squared plus x minus 1 all over 5x cubed plus x squared plus x minus 5. Okay, so now let's kind of just think of this a little differently now. We only need to focus on this stuff now, right? Because the lower powered exponents aren't going to affect our limit as h approaches infinity, or negative infinity for that matter. So I'm actually going to write a plus or minus here. So if I write my h of x, so 2x cubed minus x squared plus x minus 1 over 5x cubed plus x squared plus x minus 5. Do you guys know what I have to divide it by in order to get the limit equal to 1? It should be what? 2/5. So that's going to be my g. G is going to equal 2/5. And that can be a function. It can just be a constant. Okay, I'm going to try sort of a different challenging one with this one in terms of n behavior model, and then we will be done with our examples for today. How about we let f of x equal to x plus e to the negative x. I want us to show that g of x equals to x is a right n behavior model, I'm going to abbreviate here, for f, while h of x equals to e to the negative x is a left end behavior model for f. Okay? So I want us to show, so that means I'm telling you that the limit is going to equal to 1 for f over g and then h over g. So for the first one, for the right end behavior model, we need to calculate that limit. As x approaches infinity, positive infinity for the right end behavior model, because infinity is on the right hand side, I need to divide x plus e to the negative x over x. Now why does this equal to 1? Stop and think carefully. This is an e to the negative x power. What happens as x goes to infinity? This e to the negative x is really like a 1 over e to the x. So the denominator is getting really big. 1 divided by a really big number, that's approaching 0. So then you have x over x, and that equals to 1. So that's how we've shown the first part of this. What about the left end behavior model? Let's show this one. So here, this time the limit's going to be approaching negative infinity because it's going to the left-hand side. So we need to compare x plus e to the negative x and show that when we divide it by e to the negative x, we also get 1. Okay, so let's take a look this time. This part here with the x, as x goes to negative infinity, it's getting really, really negative, right? Think about it, it's getting really, really negative. Okay, so let's see, this is a negative number. Oops. Negative number. And now what's happening with our e to the negative x as x is approaching negative infinity? So because e to the negative x is 1 over e to the x, as x goes to negative infinity, it actually is approaching this right here. Let's see if you can understand this notation. Is this equivalent of the limit as x approaches positive infinity of e to the positive x. This is going to infinity. It's getting really, really big. Okay? But it actually doesn't matter because look, you're dividing it by itself. Okay? But I hope you guys realize in evaluating limits that this is going to infinity, that they're going to infinity at the same rate, sort of at the same time. So this is also equal to 1. Okay, so hopefully on Monday we can work a little bit more on limits, but I just wanted to touch on these two things for today.